Thank you everyone for joining this week's research talk. Dr. Reza is a postdoc research fellow at Blockchain ABC, and he earned his PhD in artificial intelligence. His doctoral research focuses on designing an adaptive public blockchain that can learn and adjust itself as network conditions change. He has a background in cryptography and holds a master's degree in artificial intelligence and bachelor in computer engineering. In addition, he spent a considerable amount of time in the financial industry, which inspired him to study blockchain technology. Since 2015, he has been involved in the blockchain industry, both in practice and theory. Prior to his academic career, he worked as an IT professional for more than 10 years. Over the past 3 years, Dr. Reza has volunteered as a blockchain lecturer and taught people about this fascinating and innovative technology. Currently, he's engaged in developing a blockchain-based decentralized artificial intelligence system to maximize blockchain's impact on everyday life. Over to you, Reza. Thank you.
Thank you, Chang. Can you hear me?
Yeah, I can hear you. Yeah.
Okay, cool, great. Okay, thanks for having me. So this is great for me to talk about this technology and the work that we did, and I'm going to do because it's not finished at that point. So let me share my screen first. Okay, so can you see my screen?
Yeah.
Okay, great. Okay, so the topic that I want to talk about this today is on-chain governance. I'm sure you heard about this a lot, especially those who are working in blockchain industry. Because if I would say the main idea of blockchain comes from decentralization. And this decentralization, it needs to be implemented in different aspects. The first aspect is decentralization in data. And that's what blockchain already implemented. In a blockchain structure, I will talk about that later in detail. We implemented a decentralized file storage. But the other aspect that we need to care is decentralization in power. And it means we have to implement a system, like a digital system, with a decentralized voting right. That means we need to have a DAO, decentralized autonomous organization. So let's say we have a decentralized company, we have a decentralized, I don't know, anything, but we need to control this in a decentralized manner. We cannot implement a decentralized app and then controlled by a single person. So from that
Hi, Reza.
point,
Hi, Reza.
yes.
Sorry to interrupt. Your voice volume is a bit low.
Oh, okay.
Yeah.
What about now?
Yeah, now it sounds better. Yeah.
Yeah, it's because of this. Okay, sorry.
Yeah, no problem.
So, I was talking about the point that we need decentralized regulation, and from that point we need governance model, decentralized governance model. This is the first practice that everybody in this ecosystem is faced. So we need to have we need to find a solution for that, and especially for the decentralized ecosystem, we have to implement a decentralized manner to do that. So what I did, it was on-chain governance model. We have to control a whole blockchain, which is decentralized in itself, and it has to be controlled by an on-chain governance model. So there is a lot of solution to implement this idea. Of course, in theory, not practice. But for the theory part as well, because the idea is very like it just recently announced, and we have to find a solution for that. There are different options to implement this idea and this requirement. And what I did, I used an evolutionary algorithm, so like PSO, particle swarm optimization, to do that. And I wanted to be specific about that one of the special issues that we already have in public blockchain. So I will talk about this. I just wanted you to know about the story behind choosing this topic and working on this. So let me start. I will talk about the introduction about the idea and some basic concept, and then the motivation that I already talked, and the problem, and also the contribution that we did during my PhD thesis, and also about the future research direction. So as I mentioned, a distributed ledger is a database. And all we know as a blockchain, as a computer engineering or computer scientist, we know when we talk about database, we already address data. But what I did, it was about voting, which is completely different from data. Blockchain in itself implemented the decentralized database. So a distributed ledger is a general term, and blockchain is one of the way of implementing that DLT concept. We also have like Tangle, which is not blockchain, is a graph-based database, and also we have a combination of blockchain and like Tangle, and also we have another implementation of DLT, which is called hash graph. So let's say we have DLT as a general concept, and then we have 3 different implementation. That's the most well-known one is blockchain. In the blockchain, as you see in this picture, there are several participants that they are participating for every single transaction or every single transaction recording. And as you see in the right picture, we have distributed ledger implementation. Especially when it comes to practice, most of example just based on financial system, because they have to implement, they have to talk about like different transaction, and they have to share those information. And those information is really important because they are financial data. And its comparison with the centralized ledger, of course, you know, that the picture talks about a lot. So in the blockchain, let me break this here. Okay. Yeah. So in the blockchain technology, for every single transaction, we need to have a consensus mechanism that needs to be accomplished before every transaction recorded on the blockchain. So let's say we have a shared space for recording transaction. But before writing any transaction, there are some nodes, there are some miners that they are responsible to come to a consensus. They have to agree on the new and recent transaction, and after that, they're gonna add this transaction to the blockchain. So from that point, you will understand there is a delay, because the larger network, the larger nodes that we have, and then the longer waiting time for adding new transaction. And that's the reason that we have 7 TPS, 7 transaction per second in Bitcoin blockchain ecosystem. So, and from this, we have an issue. Of course, you know about that scalability. So The reason that we don't have a lot of implementation in practice is the scalability issue. And this issue, it comes from this point. We have to make a consensus before every single transaction. One of the challenge that I'm going to address in this implementation, it's scalability. So I've talked about consensus. So let's say there's a group of nodes that they couldn't make a consensus. What's gonna happen? That's the biggest issue that I focused on. That there's a term we call blockchain fork, and we have two types of forks: intentional fork and accidental fork. As I mentioned, in a blockchain, any rules which is implemented in the protocol layer, it should be compatible with the whole blocks that we already added in the blockchain. So in intentional fork, let's say there's an update, there's an upgrade, or maybe there's an issue that we are going to resolve, or there's an update we are going to implement, then we have to change the rules. So we have to create a new branch of the original chain, which is called fork chain, as you see on the left picture. Then we can upgrade the rules, and from that point we have a new chain which is called fork chain. This is intentional fork, like the list of forks and updates that most of the public blockchain already have. But there's another type of blockchain fork. We call it accidental fork. As you see in the right picture, and as I mentioned, there are some point that there's a new branch in the blockchain chain. So and it becomes because of the list and the nodes, they couldn't come up with the consensus for adding a recent block. And here we have accidental fork. And what's gonna happen when we have accidental fork? We have two concurrent chain, and both of them will increase at the same time. But at some point, one of them will be discarded, and the longest one will continue, and that would be the main chain. But the one that discarded, they call it all of the blocks in that one, they call it stale block or orphan block, and all of them is just waste of time and computation. So this one, that was the idea that I wanted to focus and find a solution for that. If we can resolve this issue, then we can increase the scalability. And if we can increase the scalability, then we have larger TPS, transaction per second, and then we can use public blockchain in everyday life. So if you see, we have Bitcoin and Ethereum, and they have a lot of forks, which most of them was intentional, and some of them was like accidental fork, which leads to a new project, a new like crypto project. I want to talk about sharding as well, and then I will continue the whole idea. So in sharding, like centralized database, we have sharding in blockchain as well. A blockchain network also can be sharded, means divided into distinct segments, and each of these segments stores a part of blockchain data and processes specific transaction. This sharding, it doesn't mean has to be focused on only data segmentation. It also can focus on consensus segmentation. So let's say we have different segments with different consensus algorithms. It also increases the scalability, and I will talk about this. With sharding, blockchain network can improve the network latency and the scalability that I already mentioned. So as I mentioned in the motivation, so most of the blockchain networks, they suffer from the fork problem and network scattering, especially for those networks that they have a lot of nodes like uh, miners or validators. And this is the real issue for them. As a user, we never realize those type of forks, but it hurts a lot. Like I would say for Solana blockchain, 2 times we have network shutdown, and both of them was related to this problem. So let's say a lot of transaction come up to the chain, and they have to make a consensus, and they couldn't, and then it leads to network shutdown. So this is a real issue if we can find a solution for that. And also other impact that I already mentioned about sharding. So the problem is, I would say in simple, how to propose an on-chain governance model to reduce the forks by designing an adaptive blockchain network. So let's say we are going to have a blockchain network which is adaptive. I mean, it can be scalable based on demand. We cannot create 4 shards and then keep it on 4 shards. The number of shards needs to be dynamic because of the based on the demands that we have. So let's say there's an airdrop project on Ethereum, then we have to be more scalable. But after that, we don't need to have 4 shards. We have to decrease the number of shards, and this means an adaptive blockchain. You have to like an elastic uh, an elastic configuration for a public blockchain. And this configuration needs to be on-chain because we cannot guarantee that security that we have. So those of uh, uh, that configuration needs to be on-chain. So if we can design an on-chain governance model, then we solve a lot of issues and problems on public blockchain. I'm not talking about private blockchain because it's completely different. They are completely different. So there are some objectives that I focus on that. I already accomplished some of them, but I will continue working on that. That's the reason I'm focusing in this idea. The problem to design, the solution to design an adaptive blockchain, it's I have to formulate a multi-objective optimization problem because when we are going to increase the scalability in a blockchain, then we will lose the decentralization. There's a trade-off between these two. And then if we focus on security, then we will lose decentralization and scalability. So this is a multi-objective optimization problem that we are going to face, that we are going to have. And then, so the, the first part of the research is to define this model and formulate in a multi-objective optimization problem. And then to formulate this, then I have to find important parameters that has an impact on those on those issues that I mentioned, like scalability, sharding, and fork. So I I just uh, I just classified in the whole project in 3 steps. The first one was the fork probability modeling. So I have to provide a model for the fork rate. And then after that, on the second step, I focused on sharding and its impact on the fork rate. So let's say if we have if you have 2 shards, then the fork rate would increase or decrease in comparison to the situation that I have three that I have 3 or more shards. So that was the second step, is focusing on sharding and its impact on fork probability. And the last step, I focused on designing the on-chain governance model to define this configuration, to find the best configuration to have the best performance all the time. And then for each of the step, of course, we had already published different papers. The first step is the fork probability modeling that I mentioned. For this, there are some works out there you can find. There are some papers that they focused on blockchain simulator, because those idea and those parameters that I already mentioned is difficult to implement and change. If you want to change those roles, which is in protocol, then you have to design a new blockchain for each of them. Every single change in a protocol layer leads to a new blockchain, to have a new blockchain. So then there are a lot of blockchain simulator out there just for modifying and like working and focusing on this idea. And the second part of related work that you can find a lot of papers related to this part as well, it's blockchain behavior analysis. Some researchers worked on different updates of blockchain and behavior, users, miners, benefit, especially on the economical side. And that one also is the other part. I mentioned many times about EIP 1559. This one is one of the most important updates that's already done on Ethereum network. I call it important because it changed the mechanism for transaction fee. So it's important, and it changed the Ethereum transaction fee mechanism to an adaptive, to a dynamic model for transaction fee mechanism. So it was one of the important change on Ethereum ecosystem. So one of the related work where I found it interesting, it was proof of learning, a blockchain consensus based on machine learning competition. I would say this one is kind of far from the idea that I focused. In this part, in this work, they focused on designing a blockchain that can help to find, to train a machine learning, to provide a machine learning competition. And then those decentralized network, they are responsible to train the ML models, which is completely different. I cannot say completely different, but it's kind of far from the idea. But there are some interesting parts about the like the incentive for those participants, and I have to find I have to find the same mechanism also for when on the third step, on the last step that I mentioned, when we are going to have an on-chain governance, then we have to incentivize those learners to provide the right information. So the incentive mechanism is one of the challenge that we already face. The other one is decentralized and collaborative AI. That this one also is similar to the previous one, and they propose a framework for different participants, and they can collaboratively build an updated model based on supervised learning. And also there are another one is also similar to that idea, but this one also focused on the proof of search. So let's say for every single problem, you're going to have a set of solution which is provided by different miners or validators. And then there's a strategy to find the best one among us, like the proposed solution. We also have like other popular blockchain like Monero, Tezos, and Ethereum. They also have some part, not completely, but some part that that already implemented on an adaptive structure. So let's say for Monero, the block reward, if it, they has a they has a they have a dynamic model for defining the block reward. So let's say when there's a lot of uh, miners on that blockchain, then the size of block reward will decrease, and when the number of participants will decrease, then that reward needs to be increased because for the incentive, because to incentivize the participants. So if we have some kind of uh, flexibility, it's not it's completely different from the Bitcoin or Ethereum, but it's not complete, it's not fully decentralized, not fully adaptive. I just wanted to mention we already have some of them in even in uh, like famous and well-known public blockchain. So the first step that I mentioned, it was fork model. So for the fork modeling, as I mentioned, there is like important factors, important parameters that we need to address. One of them is the block propagation delay. So the time that takes to propagate a block in a network, and also the rate of stale block. Stale block is the orphan block that I mentioned. So the rate of orphan block or stale block is also another important parameter that we need to address in our modeling. There are two types of fork modeling that I focused and study and then implemented. And if I want to talk about the network delay and the sequence that we have when a new block generated and then propagated in a public blockchain, this is the sequence that we have. And as you see in this picture, we have different types that we need to sum up those delays to talk about network delay. And then if we can decrease the network delay, then we can increase the scalability, and also then we can like optimize the fork rate. So this one also is the EIP 1559 that I will discuss about later on. But I would say in EIP 1559, I forgot to mention, all I did, it was on Ethereum. So I focus on Ethereum ecosystem and Ethereum blockchain because this one is one of the this one is one of the important one. And if we can if we can update this, then we can find a solution for all of them. The other one of the other parameters that I introduced in my solution, it was validation degree. So let's say we have a large network and we have a large number of validator or miners, and we don't need to have all of them to verify new block. We have to decrease the number of validator blocks in every single new block. So that's the parameter I call validation degree. So in the validation degree, we have a threshold which is called theta. Theta determines how many nodes are required to validate new block continuously. In Bitcoin, this one is 1. I mean 100%. So all of the validators, miners, they need to be validate the new block continuously. But in the validation degree, theta is a parameter that determines how many of them needs to be validated continuously. So after a certain of number of consecutive nodes have accepted block, then we don't need to verify it. So they don't need to validate. This one also decrease a lot of computation and save a lot of time. And at the same time, we don't lose security and any other like important features and KPIs. So this one also needs to be addressed in our formula for the fork rate. So this is the proposed model based on, I already mentioned different important parameters. So then I just provided a formula to address all of those parameters. So we have validation degree, we have network delay, we have number of nodes, we have TB, like the block creation time, we have transaction per second, we have the number of stale block, and also we have the average propagation time for each block. So this is the formula that I use to address and count and measure the fork rate. If I found, so this is the cost function that I use for optimization problem. So here, the first step is finished, and then I have to find an optimization solution to resolve this formula. So for the implementation, I used like some fixed parameter, and then I implemented the whole idea based on those parameters that I already mentioned uh, in Python, and then I implemented Bitcoin network and Ethereum network, but I use Ethereum for my simulation and experiment. So this is the simulation. So as you know, on the left side, we have the flow chart for generating a transaction and then broadcast that transaction to a random node, and then that random node need to validate transaction. If the transaction is invalid, then they discarded the transaction. Otherwise, they added to nodes transaction. So from that nodes, there are some of them they are miners. For miners, they create a block and then broadcast the block to other nodes. This is the whole sequence for generating a transaction and generating a block and then propagation for both of them. And also we have the other, on the right side, we have the consensus mechanism. So I implemented all of this because I wanted to experiment my idea and then the solution that I found for optimizing the whole cost function. So I focused on fork analysis. Two experiments were conducted to evaluate our model. I did with two different number of nodes, 30 and 60 nodes, and this is the result. So I focused on 30 and 60, table 1 and table 2, and different parameters. And the first row is for validation degree, as I mentioned. So for validation degree with 1, uh, uh, so with theta with the amount of 1. So as I mentioned, so I mean, whole of the nodes, they need to be validated transaction, but the best one was 0.5 based on the experiment and the results. So, I mean, we don't need to have all of the consecutive nodes to validate every single transaction or every single block. Only half of them, they need to validate. This one decrease a lot of time and computation. And also for different types of network delay. And as you see on the last row, we have our model, our cost function for different parameters, and then I will show the picture as well. So I did two different experiments based on two different number of nodes, and as you see here, the validation degree and the uh, different parameters as I use. So you can see on the top right picture, we have validation degree. As we increase the validation degree, then the network delay will increase, no matter how many nodes that we have. So this is the main parameter that I mentioned. Again, we have this, okay, I forgot to mention, I did experiment in two parts. First one before EIP 1559, and the second part was after that, because that was a big change and update on Ethereum network. Again, in here, based on EIP 1559 compatible of network, also we have the same result: higher marginal cost and larger step reduce the network delay. And when we have the reduced network delay, then we have fewer blocks that are required additional time to complete their block. This fact leads to decrease the fork rate. And then, as I mentioned, when we decrease the fork rate, then we increase the performance, and then we increase the scalability for blockchain. The second part was on sharding and its impact on fork probability. I have to add implementation of sharding and then do the experiment again and again. Here is the result for based on the sharding. So I focus on 4 shards, and then I did different experiment based on like 1 shard, 2 shard, 3 shard, or 4 shards. But here is only for a specific shard. So let's say the fork probability on shard 1, shard 2, or shard 3 and 4. And this one and those parameters for each shard, all of them just specified and determined randomly. And I did a lot to find the average amount. But here we can see the interesting result. So you see the average, the first row on the left table, we have number of shards. As you see, when we increase the number of shards from 1 to 4, then we have the average fork probability will be decreased. So that means when we increase the number of shards, then the fork rate will decrease. And this is the interesting finding. If we can design the adaptive blockchain that can increase or decrease the number of shards, the number of shards based on demand, based on network congestion, then we can decrease, then we can control the fork probability. And that means we can control the scalability, and also we can control the performance. This is the idea. And also we have the same structure, we have the same pattern for different number of nodes. So in this part, I did experiment with 6 nodes and 120 nodes. We have the same pattern for 120 nodes. You see, and when we increase the number of shards from 1 to 4, then we have the average fork probability will decrease from 0.99 to 0.527. And also we have the same result on chart. You will see when the number of shards, like as I mentioned, increase, then we have the network delay decrease, then we have the average of orphan block will decrease, and yeah, the average fork probability also for sure will decrease. So I would say comparing the result from the sharded network to non-sharded network, the probability and the number of orphan block have significantly decreased. And like I mentioned, increasing the number of shards result in a lower fork. So I would say so far we modeled the fork model, we formulate the fork model, we did experiment and find the best correlation, the best correlation between those parameters and the fork rate. So here it is. We have to design the on-chain governance model, and then based on PSO. So we know the cost function, we know the parameters. Then in this step, we just need to add some learner nodes that they have to be responsible to finding the best solution, to finding the best configuration at the same time. So I would say I just wanted to introduce, talk about PSO a bit. So in the PSO is an algorithm based on the concept of swarm intelligence. So the goal of an optimization problem is to determine a variable represented by a vector. So here we have that vector. We have a list of parameters, which is really important for the fork probability and scalability issue. Each particle would be able to adjust its flying according to its own flying experience as well as the other particles experience. So we have a general experience, and then we have a private. So let's say we have a private experience and we have a public experience. We also have the same in our optimization problem. So there are some works research that they also focus on this idea, but not the way that we looked at it. They just focus on maintaining a balance between block composition time and transmission time. And I would say this also focus on the network delay, but none of them focused on designing that on-chain governance that I mentioned at first. So okay. Here on step 3 and 4, we have a learner committee consensus. So we developed a committee consensus among learner nodes, which is really different from the other nodes that we already have. And those committee learner nodes, they are responsible for executing the PSO optimization algorithm independently based on their local experience and local input that they have. And then after this learning period, they have to share the result, and then we have a general model updated. And on step 4 also we have dynamic sharding, as I already mentioned. The number of shards also will be dynamic based on the result that we got from step 3. So that learner committee consensus, they are responsible to determine the number of shards on a specific time. So let's say when we have a traffic congestion for transaction in a public blockchain, then the number of shards needs to be increased. So I talked about the potential impact, and then also talked about the proposed model, the PSO optimization that we use. And I also talked about a new node that we are already added and call it learners. Also, I talked about different parameters that we are going to address in our optimization problem: validation degree, average block size, miners, marginal cost, which is like transaction fee, and the average time blocks. So we have inputs that I mentioned, and then we have optimization problem. As I mentioned, each learner, they run the complete PSO independently, and then they have their user experience. After that, we have different solutions proposed by learners. Then we have an aggregate mechanism to find the consensus between those learners. The consensus process, for this part, I use a weighted average mechanism. For that committee, the solution is weighted by the sum of the hashes produced by all miners connected to it. I mean, I focused on the hash power and the power and the share of each miners to participate in a blockchain. And also I have another parameter, which is learning frequency factor, will be considered when we need to update those parameters. So in my implementation, I assume this parameter by 4. I mean, then after each 4 consecutive blocks, we need to determine the optimal value. Then we need to update the parameter. So here is the cost function that I mentioned. So we have two terms. The first term is for the fork probability. The second term is for the user experience and the overpayment, and focus on the transaction fee. And this is the flow chart that I mentioned. And here's the result. So again, we have the same pattern: number of shards, the average number of fork blocks. And you see when we increase the number of shards, the average network delay will decrease significantly, and also the average number of orphan block as well. So here is the sharded network. So based on iteration number, this is only uh, for one of the member of the committee member. I just wanted to show the mm, the convergence graph. So as you see, based on the iteration number, the cost value will be converged. So and I did the experiments based on the different number of shards. So here we can see for two shards. So in one shard, it means we don't have any shard. So I just wanted to focus on this part. So for two shards and three shards, as you see, when we increase, so for every single shard, we have validation degree and those parameters at the same time. But based on the picture you see on the left side, the proposed model sometimes increase or decrease the marginal cost. The marginal cost, it only represent the transaction fee to reduce the fork probability or improve the user experience. So we have, as I mentioned, we have a multi-objective parameter. We have a multi-objective optimization problem that sometimes increase or decrease different parts only to address the current situation of network. So based on this implementation, we have an adaptive blockchain that can increase or decrease different parts based on demand, based on the real-time experiment. Here again, we have for three shards. So we have the marginal cost graph for all shards. You see we have a decreasing trend, even though it's not beneficial for user, may result in a higher probability of fork. So sometimes we lose the fork rate, but we save the transaction cost. We save transaction fee for the user. This is what happens in the real life. Sometimes as a user, you're going to pay a lot transaction fee, but we have to make sure the transaction will be finalized. So this is what happens in real life. And again, we have the same experiment in our implementation. Yeah, so again, we have the same pattern for shard as well. Reducing the average marginal cost would improve the user experience, because from the user standpoint, decreasing the transaction cost is great, but would increase the fork rate, which is not great in terms of security and scalability. So due to this issue, the on-chain governance model has increased the average time block between two consecutive blocks. So this is how this algorithm works. The on-chain algorithm works based on different parameters. It justifies the configuration. So if I want to sum up with the idea, we presented a model for the fork probability, which is more effective parameter included like validation degree, network delay, and the average time for block propagation. We found that increasing validation degree will result in a significant propagation delay, and which in turn will increase the likelihood of fork occurring. And also we talked about what happens when we decrease the number of shards, And also we talked about to improve security, speed, and efficiency and blockchain network in a sharded blockchain. We have to control the fork rate. And I would say, according to result, adding a shard reduced the number of orphan blocks by 60% on average, which is really great. And based on this result, we can define and design different parameters for an adaptive blockchain. So future research direction that I already picked one of them is different part of, so I focus on proof of work in this implementation, but there are other consensus algorithm like proof of staking or delegated proof of staking that we can focus on that as well. And also I focused on scalability. I focused on like fork rate decreasing, but we can also focus on especially on scalability and also decentralization, or maybe even more than that, a multi-objective that can address all of them, scalability, decentralization, and security at the same time. So this one also is one of the other direction that we can focus on. That we can focus for future research direction. So that's it. I would be very happy if you have any question, and thank you.
Thank you very much, Reza, for the wonderful presentation. Any questions? If you have questions, either you can type the questions in the chat, or you can just open up your microphone and speak to the microphone. Okay, so if there's no question, then let us thank Reza again for your wonderful work. And if you want to continue the conversation with Reza, please reach out. Oh, yes, there's a question from Yuji. Yeah. Oh, okay. Yuji is just giving a applause. Okay. Okay. On that note, then thank you, Reza, for your work, and thank you everyone for joining us today. I hope you have a wonderful day. And if you want to continue the conversation with Reza, please reach out to him. We have his contact email on Blockchain UBC's website.
Yeah, thank you. Thanks everyone. Yeah, as mentioned, if you have any question, so just reach me out.
Okay, great. Okay, thank you everyone. Bye-bye.